Today we are going to see the trends in ionization energy. We have trends down the group, and we have trends across a period. If we look at trends down a group, for example, we are going to take group 1 as an example. The first, of course, this is trends in the first ionization energy. So if we want to find out the trends in the first ionization energy down a group, we are going to choose group 1 as an example. Group 1, we have lithium, sodium, potassium, rubidium, and cesium. We will see that the ionization energy decreases down a group. Ionization energy decreases down a group. Why does it decrease down a group? If we look, for example, at lithium, lithium consists of 3 electrons. So it has, this is the positive nucleus, it has 2 electrons in the first shell, and it has an electron in the last shell. So instead of drawing circles representing the shells, I'm going to draw just arcs. This is the positive nucleus, this represents the first shell, and this represents the second shell. So if we look at lithium, we'll see that it has a +3 positive charge, but it has 2 shells. In the first shell, of course, we have 2 electrons, and in the second shell, we have only 1 electron. And since all these elements are present in group 1, we'll see that all of them will end up with 1 electron. So here for sodium, it has +11 protons, and it has an electron at the outermost shell. The potassium also has an electron in its 4th outer shell, has an electron. Rubidium has an electron in its last shell, and also cesium the same. But if we look at all these elements in this group, we'll find that as we go down the group, the nuclear charge increases. So here, although the nuclear charge increases down the group, although it is increasing, it was expected that the attraction force between the electrons and the greater nuclear charge will increase. And this is correct. The attraction force should increase. But there are 2 other factors that compete with this factor. We have 2 other factors. The first factor is that the outermost electron, or the valence electron, is further away from the nucleus, is further away, or we say gets further away from the nucleus, and the shielding effect increases. The shielding effect increases, and this makes the ionization energy decreases. Now we want to see here, we say that although the nuclear charge increases, this means that as we go down the group, as you see here, the positive charge increases. And this means that the attraction force between this positive nucleus and the electrons, the outermost electron, also increases. But there are 2 other factors. The first factor is that the valence electron gets further away from the nucleus. If you look at this electron, it's further away from the nucleus compared to this electron in case of lithium. We'll see that the distance here is so small that the attraction force is greater, but in this case, the attraction force is smaller than the first, because the distance between the outermost electron and the positive nucleus increases. And when the distance increases, this means that the attraction force between this outer electron and the nucleus, the attraction force decreases, and it will require less amount of energy to remove this electron because it's further away from the nucleus. The attraction force now is not as strong as the attraction force in case, for example, in case of lithium or in case of sodium, where the outermost electron is very near to the nucleus. Here, in case of lithium, the outermost electron is very near to the nucleus, and it requires a big amount of energy to remove it. The attraction force is the strongest. It's very near. But here the electron, the outermost electron that is going to be removed by the first ionization energy, we see that the distance between this electron and the nucleus is so far that the attraction force becomes the least, and it requires less amount of energy to be removed. And the second factor is the shielding effect. What do we mean by the shielding effect? The shielding effect is the effect of the innermost electrons. The shielding effect is the effect of the inner electrons. The inner electrons in these inner shells. If you see here, we have electrons in all these shells, and the electrons are moving in between the innermost, the outermost electron and the nucleus. There are a lot of electrons in between this outer electron and the positive nucleus. And these electrons shield the effect of the positive nucleus than this outer electron. They prevent the attraction force or the effect of this nucleus on this outer electron. These electrons are moving in their shells. We have 2 electrons, 8 electrons, 18 electrons, 32 electrons. All these electrons are rotating around the nucleus. They shield the effect of the nucleus on this outer electron. And this will also contribute in that the energy required to remove this outer electron will be the least. Whereas here, the shielding effect consists of only 2 electrons. These 2 electrons shield the effect of the nucleus than the outer electron, but not as much as in case of cesium. We have a big number of electrons that shield the effect of the nucleus than this outer electron, and that's why as we go down the group, the ionization energy decreases. It requires less amount of energy to remove this electron. So this happens in all groups. Down all groups, we will see that the ionization energy decreases. The first ionization energy decreases. Now, what happens across a period? If we are talking about the ionization energy, the first ionization energy across a period, we said last time that across a period, going for example, from period 2, starting by lithium, we have beryllium, we have boron, we have carbon, nitrogen, oxygen, fluorine, and neon. We said that as we go across a period, as a general trend, the ionization energy increases. Why the ionization energy increases as a general trend? We said because all the elements in period 2, their last electron is filled in a second shell only, in 2 shells only. So here, in case of lithium, we will see that we have a +3 nuclear charge, and we have 2 shells. The first shell is filled by 2 electrons, and the second shell is filled by 1 electron. In case of beryllium, we have 4 positive charges inside the nucleus. We have also 2 shells where the first shell is filled by 2 electrons and the second by 2. In case of boron, we have a +5 charge, and we have 2 electrons filling the first shell and 3 electrons filling the second shell, and so on. We always we are filling the second shell by more and more number of electrons, and more positive charge is increased. So we said that as we go across a period, the ionization energy increases because the positive charge or the nuclear charge increases as we go across the period. The positive charge increases, and also the electrons, the number of electrons increases, and so more attraction force between the positive nucleus and the outer electron. And this means that it will require more amount of energy to remove this electron as the nuclear charge increases. And the shielding effect is the same, because the shielding effect is caused by only the electrons present in the first shell. So the shielding effect is the same. It's only the shield due to 2 electrons in the first shell. But we see that as we go across the period, the nuclear charge increases, the shielding effect is the same, and so it will require a bigger amount, or the biggest amount of energy to remove the outermost electron from neon than to remove it from any other element in the periodic table. So the ionization energy increases. But we have exceptions in case of going across a period. We have exceptions. What are these exceptions? We will see that we have exceptions between groups 2 and group 3, and between groups 5 and group 6, we have exceptions. What are these exceptions? If we look, for example, at beryllium, which is present in group 2, it has 4 positive nuclei, positive nucleus, and it has a +4 nuclear charge, and it has 4 electrons. And it was supposed that the ionization energy of boron, which has 5 nuclear charge and 5 electrons, to be higher than that of beryllium. But the opposite was found. We will find that the ionization energy of beryllium is greater than the ionization energy of boron, although it was supposed that the boron to be greater than that of beryllium. Now, why is this? Why does this happen? If we look at the electronic configuration of beryllium, we will see that it is 1s2, 2s2, but in case of boron, it is 1s2, 2s2, 2p1. So we will see here that the electron to be removed in case of beryllium, it is removed from a 2s subshell, but the electron to be removed in boron is removed from a 2p subshell. And we see that the electron present in boron, the electron to be removed that is present in boron, is present at a higher energy, which is the 2p subshell. So the electron present in the boron is at a higher energy than the electron to be removed from beryllium, which is present in a 2s. You will see that the electron in boron to be removed, or we can say here to the boron to be removed, is present at a higher energy subshell. So whenever you have an electron that is present at a higher energy subshell, this means that its distance away from the nucleus will be greater than the distance between the electron present in the 2s subshell and the nucleus. You see here that the distance between the 2p electron and the nucleus in boron is greater than the distance between the electron to be removed in beryllium and the nucleus. Since the distance is further away, this means that it will require less amount of energy to remove this electron because it is further away from the nucleus. Also, if we look at the shielding effect, we will see here that the shielding is caused by the electrons present in 1s and 2s subshells. So we have 2 shells forming shielding effect between the outer electron to be removed in boron and the positive nucleus. But in case of beryllium, we will see that the shielding effect is caused only by the 1s electrons. Here it is caused by the 1s electrons and the 2s electrons. And since the distance between this outer electron and the nucleus is greater than the distance between this outer electron in beryllium and the nucleus, and also the shielding effect here is greater than the shielding effect in case of beryllium, we will see that it requires less amount of energy to remove the electron in boron than to remove an electron in beryllium. Now, when we look at groups 5 and 6, the second exceptions, for example, if we look at nitrogen 7 and oxygen 8, it was supposed that the nitrogen to have a lower first ionization energy than that of oxygen, but we will find that the opposite happens, that nitrogen has a higher first ionization energy than that of oxygen. Also, to explain this, we have to look at the electronic configuration. In case of nitrogen, it is 1s2, 2s2, 2p3, but in case of oxygen, we have 1s2, 2s2, 2p4. So if we look at this last subshell, we will find that we have 3 electrons present in the p subshell. But if we look in case of oxygen, we'll find that we have 4 electrons in the p subshell, and so there are 2 electrons filled in the same orbital of the p subshell. And the presence of these 2 electrons present at the same orbital in case of the p subshell, in case of oxygen, this causes repulsion between these 2 electrons. Both electrons are present in the same orbital, so repulsion will take place between them, and this will make it easier and requires less amount of energy to remove one of these electrons. So we say that the electron to be removed in oxygen, the electron to be removed in oxygen is present as a pair, in the p subshell, or in a p orbital, in the p orbital. This causes repulsion. This causes repulsion between the 2 electrons and requires less amount of energy to be removed, and requires a less amount of energy, or first ionization energy, to be removed. So when we compare an electron to be removed in oxygen or in any electron in group 6 compared to the removal of the outermost electron, by the first ionization energy in case of any element in group 5, we will see that the ionization energy in group 6 is lower than that of group 5, because you will see that when we write the electronic configuration of, for example, oxygen, which is present in group 6, there are 2 electrons paired in the same p orbital, and this pairing of electrons, these electrons will repel each other, and it will require less amount of energy to remove one of them. But here, each electron is present separately in a separate orbital, and they are very stable in this way. As you remember, we said before that if we have a subshell that is half filled or completely filled, this will give it greater stability. So you see here that each electron are present alone, and the p subshell is half filled. This gives it greater stability. It requires more energy in order to remove one of its electrons. But here, due to the repulsion between these 2 electrons present in the same orbital, this will make it easier and requires less amount of energy to remove one of them. Of course, the same trend happens in any element present in group 2 and group 3, and any elements present in groups 5 or 6. And if we take, for example, period 3, if we talk about period 3, we have sodium, we have magnesium, we have aluminium, silicon, phosphorus, sulfur, chlorine, and argon. We'll see the same trend happening. If we look as a general trend, we will see that the ionization energy as a general trend increases. The first ionization energy increases across the period, but between magnesium and aluminium, we'll see that magnesium will have a greater first ionization energy compared to aluminium for the same reason. If you look at the electronic configuration of magnesium, it is 1s2, 2s2, 2p6, 3s2. But in case of aluminium, it is 1s2, 2s2, 2p6, 3s2, and 3p1. So of course, the 3p electron is further away from the nucleus than the electron present in the 3s in case of magnesium. And so the attraction force between this outer electron in the p subshell of aluminium, the attraction force between it and the nucleus is less than the attraction force between the electron present in the 3s and the positive nucleus in case of magnesium. The distance is further away than that in case of magnesium between the outer electron and the nucleus, and also the shielding effect here increases. Here we have 1, 2, 3, 4 shells or subshells shielding the effect of the nucleus away from this outer electron. But here we have only 3 subshells shielding containing electrons that shield the effect of the nucleus away from this electron. And so we will see that the first ionization energy to remove this electron in case of aluminum is less than that of magnesium. And also, if we look at phosphorus, if we compare phosphorus with sulfur, we will see that the electronic configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. But in case of sulfur, it is 1s2, 2s2, 2p6, 3s2, and 3p4. So if we draw the electrons present in the 3p subshell here, we'll find that each subshell, each orbital contains 1 electron. But in case of the 3p subshell, in case of sulfur, we will see that we have at the beginning 3 electrons, and the 4th electron is filled here. And since this 4th electron is filled in the same orbital as that of another electron, they are present together in, there is a pair of electrons in the p orbital. This pair of electrons will repel each other. And due to this repulsion, it will require less amount of energy to remove this outer electron. So these exceptions are present whenever we have any period. You have period 3, you have period 2, you have period 4. For the main elements, whenever you have the same, period, then at any period, the first ionization energy as a general trend increases from left to right, from the first element present in the period to the last one. But there are exceptions in all the periods between groups 2 and group 3, and between groups 5 and group 6. So this is the trend in ionization energy.